Yo, testing, 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 testing. Is this on? Are we on? Are we ready? Okay. Yo, cool. My name is like Menace. Short for Menas Katlunga. Kidding, bro. I would never do that shit. Anyways, आज का stream is gonna be like mostly for accountability. Like, huge part of the stream is gonna be relevant to the viewers, which are zero precisely. That's also one of the reasons why I can get away with this stream. But uh, I'm just gonna study this stream. Y'all will just see me going through some textbooks, reading through some rigorous, somewhat rigorous definitions, uh, trying to solve some hard math problems, I guess. Not math problems, algorithm problems, not hard problems. Honestly, it's just gonna be, you know, getting good and planning how to study, I guess, for the exam. So I've got the lectures and shit in place. When I do view lectures, y'all can't view them with me. Y'all will just have to pretend that y'all are watching, but y'all will probably just see me take notes, and that should be good enough. What else? What else? What else? Yeah, man, that's it. And in the middle, I might go move around, pee a little bit. I might go and do some stupid shit. But anyways, let's start with this. I also need to get some printouts for posters that I want to stick on my wall. Uh, I have some quotes and shit, motivational quotes and shit that I want to put up. Uh, I usually write them down, but get some of them are like in form of a tweet. So getting a printout would be much better, much better. Cool. So cool. What I'm gonna do is, can I mute? What if? Whoa, whoa. Okay, testing. Okay, I realized that I can just mute myself. I'm just wondering, how can I? Okay, if I mic and aux, if I just close this, it works. Stream browser, mic and aux, Meniscat. Oh, okay. So if I do remove, interesting. So desktop audio. Okay, so if I remove mic and aux, I'm just gonna quickly hop over to the live stream and see what happens. Cool. I was just testing, and I'm gonna go to the live streaming software and just see if um, I'm just gonna see if it catches me doing this. Like if it catches that um, muteness or something, whatever. Hold on. Form of a tweet. So getting a printout would be much better, much better. Cool. So cool. What I'm gonna do is, can I mute? What if? Whoa, whoa. Okay, testing. Okay, I realized that I can just mute myself. Just wondering, how can I? Okay, if I mic and aux, if I just close this. Beautiful, beautiful. Stream browser, mic and aux, Meniscat. Oh, okay, so if I do remove, interesting. So desktop audio. Okay, so if I remove mic and aux, I'm just gonna quickly hop over to the live stream and see what happens. Cool. I was just testing, and I'm gonna go to the live streaming software and just see if I'm just gonna see if it catches me doing this. Like if it catches that um, muteness or something, whatever. Hold on. Getting a printout would be much better. Okay, beautiful. So my test is successful. I can now kind of see that uh, my streaming software is set up ready properly. I know I can just like click on mic and aux, and it just mutes myself. which is good, which is what I wanted. So I'm gonna go through my lecture again and just keep taking notes. So in the meanwhile, maybe I could just write a message if someone by chance ever hops in. Oh, hold on, okay. Shiv is watching your lecture. Cool. So this maybe not. I should just stick to my stage name, which is Menace Cat is watching a lecture. Is probs on mute or not speaking much? Right, this is what we will keep here. Boom. So if someone hops onto the live stream, they'll probably just see this. And what I will do is I just need like a page I need like one page place to put all my docs, I guess. Hold on, give me a sec. This is my Anki. Anki's fine, I guess. So we'll do this real quick. Grad Algos notes, cool. So I'm gonna open my Steam browser. So maybe I can just like copy this. Oh wow, what the fuck? Did I break this? Huh, something happened here. Why did this just go blank? That usually doesn't happen, right? My collection is excellent, so this shouldn't be a problem at all. What the frick, bro? So I copy this. Why is Google Docs like misbehaving, bro? Yeah, reload please. So Google Docs is fine. Job prep analysis is also fine, I guess. It's just interesting that I get the exact data structure for Excalibur. Cool. Anyways, so just maybe can copy the text here. Okay, so Menace Cat is probably doing this. So just make this title. So in case someone comes here, they'll just see this. Anyways, cool. Without wasting more time, I'm just gonna go back and start watching my lectures. Life ain't so easy. Let's see, I'm gonna do a recap of what all I've studied so far. I've studied Grad Algos. Okay, I've studied graph representations, adjacency matrix, adjacency lists. I've studied DFS, the time complexity for DFS, some observations around DFS. I've studied edge categorizations like tree, back, forward, and cross edges. There are some observations around the edges. That such as back edge only exists in a cycle. Depending on the order you decide for the graph, the edge categorization will change. Okay, this is all in a directed graph. What else have I figured out? Like the modifications that you need to do to DFS with pre-order and post-order counter to get the backward, cross, and forward edges. So that is in place. I have some observations around pre-order and post-orders. I was at the topological order, right? Topological order is essentially the post order after DFS traversal gives the topological order. That's what we know. Cool. Let's continue.
I add some kind of queue. And then while the queue is not empty, I say, okay, give me some vertex, which is, let's say, give me an element on a queue of something, right? Mark it as visited. Let's say if on a queue of something, right?
Basically, you're guaranteed to get this left the right thing because you visited everything that's reachable to that vertex.
So the point of DFS was that if you call this thing, everything that can be reached from here is going to be visited. So let's say I call this for every single neighbor. After I'm done with my for loop, I know everything was visited that can be reached from all the neighbors. So everything that is going to depend on me will already have a post number because I managed to go back from my recursion. I'm only assigning a post number to my vertex after everything that depends on me has already been visited. So the post order gives me this relative logic order. All right, 5 more minutes. So I'm going to do very quickly DFS because there's one exercise in this and I need to know the DFSs. So DFS here is a recursive algorithm. I can also write that as an iterative version. Yes, more things. DFS starting from some vertex, non-recursive variant. I add some kind of queue, and then while the queue is not empty, I say, okay, give me some vertex, which is the same. Give me an element on a queue or something from it. Mark it as visited. Let's say if visited, if it was already visited, I don't need to do anything. So let's say next or continue with the language you use. To say in my while loop, don't do anything with another iteration. Otherwise, mark it as visited. And then iterate with all of the neighbors.
Okay, so what we've done is simply, well, the queue is not empty. You get a vertex from the queue. If the queue is visited, you go ignore it. Otherwise, you mark it as visited. And for the neighbors of V, you just add them
If
to
the queue here is a
Sure, that's easy.
What's it called? First in, last out.
That would be DFS, right? The DFS.
So he's using queue in a very general term. He's calling the queue having like he's using queue and stack interchangeably. So he says if queue is first in,
Last out.
last out,
Also called
then it's a
stack.
It's a stack. Yep. First, hold on. So isn't stack last in, first out? What is first in, last out? That is also a stack. Lol. Okay, cool. Interesting. That's actually such an interesting thing to note down. So again, I'm just gonna go here. Quick notes, I guess. I have a lot of notes on a piece of paper here, but I'm just gonna note them down here as well. So if I'm like DFS of, actually I don't want to call it DFS. I'm gonna call it like traverse. Okay, I'm just gonna call it trav of V. It's just gonna be some generic function, and if you go through V, and then you're like, hey, if V in visited, or let's just call visited as a set. So if visited of V is true, you can just say continue, right? Actually, hold on. Let's just do this. Let's just call this trav equals like some list. Okay, this is gonna be like some list while trav, right? While trav V equals trav dot pop, get something out from the trav, like, then hold on, if V in, okay, if visited of V is true, return, or no, not return, continue. We don't return at all. We just say continue. Keep looping. Just don't go to the next section of the code. Just go through the loop. And now for neighbor U in U of V, if U is not, okay, if visited of U is false, that means that the U is not visited. You just do V dot append of U, right? And and that should give me my but the question is, do I need to have this condition? Like, do I need to have this condition? If the neighbor has been visited by someone else, can it happen that the neighbor is visited by someone else? So even if I do this condition would anyways get rid of it. So this is a redundant condition, right? Because eventually it will be like, hey, uh, this should be trap. My bad, my bad, my bad. This should be like this. So yeah, this should be good. This should be good. Now, let's see. Okay, cool. Now, if trav is philo or lifo, which is first in, last out, or last in, first out, then trav is a stack. If trav is first in, first out, right? If trav is first in, first out, or last in, last out, FIFO or Lilo, then trav is a queue used for DFS. So that's like a simple way of defining this, I guess.
And this is equivalent to the kind of isn't a DFS. Okay. Let's say, oh, maybe this is also DFS. Then
First in, first out, okay.
both of these, then from like, then you visit everything of this will be
theoretically correct.
Okay, cool. So we have seen this lecture. I just wanna like revisit the topological
it's
order.
going to be smaller than the pre-order of U.
Okay, so we know topological order is pretty straightforward. Hold on. So we gotta get back. I'm just gonna quickly note this down in my doc. So while Q is not empty, okay. If visited, we continue for U for neighbor U of V, Q dot append of U. Alright. So now that we have done this, we gotta be like, okay, hold on. So now that we've done this, we'll just be like, if Q is LIFO or philo, then it's DFS stack. If Q is FIFO or LILO, then it's BFS, a standard queue, right? So this is how we note this bitch down. Cool. So there's not a lot of okay, so there is not a lot of like stress on whether or not topological order is very like key to these lectures, but we'll just ignore it because everyone's ignored it. And now we will go to the next lecture, which is on graph traversals and shit. Yo, cool. Oh shit, I have another lecture, I have another call. So like if I just do like group me, come on man, I don't wanna like log in every time. It's so stupid. No, I need to do like a lettuce cat, lettuce meat or something. Let's see, I need to do some. Is this? So this is like September of 2024. Thursday is I have an exam, so Friday I can do add availability. So Friday there is something on Monday. I guess Monday I can do everything. I guess Monday I can do the whole day. I guess Tuesday, can I do Tuesday? I have like some lecture on Tuesdays. Like I have lectures like till 3, so that's okay. Wednesday should also be pretty good. Oh my god, dude, there's so much availability that I have to put in. Okay, hold on. I'm just gonna quickly check what. So it's like the next 2 days, I guess. So I know this is one, this is Fridays are pretty good for me. Yeah, okay, fine. Fine. So this is good. I'm just gonna be like till 1, everything's okay. But Fridays, rest of the entire day is okay for me. For Fridays, okay. So till 2, next shift. Yeah, that's good. So I've added my availability as well. So this is pretty good. What else do we gotta do? Okay, cool. So back to the lecture. Whew. So gonna set this notes aside for review, I guess. So this is gonna be set aside. This is open horizon stuff, which is okay. So this is page 1. This is page 2 of my notes. This is like my graph notes and shit. So the real topics will now start from here, which is like a little harder, I guess. Let's see. Hold on, I'm just gonna have to mute myself for a second. Give me a break. Yo. Hold on. My throat's like kind of acting weird, but fuck it. Hold on. Muting myself. Okay. Okay, baby girl. Cool. So now that we are back, let's get started with the lecture real quick. Come on, bro. Don't do that to me, bro. 1.5. This is like a 1 hour 21-minute lecture, so it should be a heavy one. Yeah, that was fine. I think I've gotten the perfect I think this is perfect. Hold on, this may need little adjustment. Perfect. Perfect. No, no, no. It's really perfect. Actually, you can try. Okay, we're doing search algorithms then. Cool. Cool. Yo, hold on. What the fuck? What the fuck? Okay, it's working. It's working. It's working. Cool. Why does this not start?
Empty visit the vertices in the queue.
Okay, so general search algorithm search for a vertex tree.
So you just go over the queue and you check, did you visit this vertex? Yes. If you already visited it, then you don't do anything. So this is, you can think of that, for example, as like an iterative version of the DNS we had last time. So it depends a lot on what kind of queue data structure you're going to use here. So if you have a last in, first out queue, which you also call a stack, then you get DNS. If you use a regular first in, first out queue, then you get first search. But you could also use, for example, some kind of priority queue. And then it depends on what kind of priority you use. Depending on what choice you pick for the priority, you're going to get a whole bunch of different algorithms for this. Let's say tons of different algorithms.
So this one's going to be about priority queue. So okay, so hold on. This is actually a very good one because if I go back to my trav function, right? I'm just gonna call it like search function, search array. Cool. So and this holds still. This holds. Cool. Now, if search is a priority queue, then you start moving beyond DFS or BFS. Like that's essentially when you get to search, I guess. Cool. Let's watch this without any interruptions. I don't wanna like. Come on, dude. Okay. Anyways, this is annoying. Yeah. Cool.
Which depends on what you pick as priority mode.
I get it now. Oh my god, I did mess up one very important thing, very key thing, which is once I do this, I got to be like visited V. So this was very important. I almost had forgotten about this. Important. Don't forget to mark this visited. Right, so this can't be just missed randomly. Cool. Okay, hold on. So we got a DFS. Okay. Hold on. We gotta make a master list of mistakes that I have made. Let's see. While writing the DFS iterative, DFS, BFS, search iterative algo, I forgot to write about forgot to mark the node as visited. So I think I'll just do one thing. I'll make this numbered, and so I'll just do this. Mistake 1, right? So we want to ideally have a way to refer back to these mistakes after our study session, so that like when we go back we don't make the same mistakes. So cool, this is like the first mistake that I made. So if I write this shit in exam, they're gonna screw me real bad. Cool, continuing.
And today I want to give a whole bunch of examples, some different algorithms for this priority queue example. First, I want to go quickly again over BFS because I didn't have a lot of time on that on Tuesday. This is one exercise question. So just make sure that everyone has the necessary background on BFS. I'm going to do more details on BFS. But for now, is the high-level idea of this code. What is supposed to do? The idea is just that if the queue is the bunch of vertices that you want to visit, you do visit everything only once. And whenever you do visit a vertex, you just add all the neighbors to your queue. So let's start with first in, first out queue, which gives us BFS. Let me just draw an example graph saying some start vertex S, A, C, F, other vertices. These are the edges of my graph. And I run my algorithm starting use my first up queue, which gives me the DFS algorithm. And here I'm going to list the queue, and initially my queue is just the vertex S from which I start. When I visit the first vertex, when I iterate over all the edges, I check all the neighbors. So I'm going to add A, B, and D to my queue. Next, I'm going to add A, B, and D to my queue. I've already visited S. So my queue now only contains A and D. And it's the first up queue, so I'm just going from left to right in the same order as I added them to my queue. So next I'm going to visit A. I'm going to visit this. I'm going to iterate over all the outgoing edges. There is an edge going to B. So I'm adding B to my queue. I don't care that it's already there, I'm just adding it again. Next, maybe I'm also going to mark this as the edge that I used. So I'm going to visit E, which came from this edge here. Visiting E. I look at all the outgoing edges. I have an edge going to A, I have an edge going to C. Adding A to my queue and adding C to my queue. I'm looking at the next entry in my queue, that's D. Just so because of this edge here. I visit D and look at all the outgoing edges, and look at D and E. So the outgoing edges that I see, add up to my queue. And on the next case, I'm going to look at E, but I realize, hey, if it was already visited, I'm not doing anything. If E was already visited. So I look at B, realize I don't care about this vertex, and I just go to the next thing in my queue. I look at vertex A, I also visit A already, not doing anything here. And then when I see C, I see vertex C, which is in the queue because of the edge that I visit when I visit B. So I'm looking at C, and mark it as visited. It doesn't have any outgoing edges, so I'm not adding anything else to my queue. Then vertex D, again, hey, I already visited this, I don't care about that one. And then I'm looking at E, visit this vertex, look at all the neighbors of E, and F, my queue. And last, I look at my last edge of the queue and visit F. Then I visit back. The important thing here is that I have the order in which I visited things was, let me highlight these ones here.
Cool, this is from the lecture.
This vertex S, that's where I started. So in a sense, that kind of has distance 0. And the next group of vertices that I looked at, A, B, and D, those are all vertices that have distance 1 from my start vertex. Then the next group, at least the vertices that I did visit, C and E, they're all the vertices where I have to take 2 steps.
There's a notion of distance. Okay, hold on. This is
At least the
important.
vertices that I
Let me calculate the distance myself, perhaps, just so that I know what I'm doing. S, A, B, C, D, E, and F. This is how things are moving right now. B goes to this, D goes to B, D, F, S goes to D. So I know that S is my first distance. It's gonna be 0. Then all of my S's. Okay, so distance is essentially distance from the very start node, right? Is that what it means? So okay, so this is done. Then A, B, and D are appended. Now all of A's neighbors are appended, which is like B. That's the only neighbor. A is done. Then I will look at B's neighbors, which is like A and C. So B is traversed. Then I'll look at D's neighbors, which are again B and E. And then this is done. That draws a boundary. So B we'll check all of B's neighbors. A is already visited. So it says, so B is already visited, so we don't visit B. A is already visited, we don't visit A. C is visited, so C has no neighbors, so we don't visit C. B is already visited, so we don't visit B. E is already visited. E is not visited, so we check E's neighbors, which is F. So this is how we get it. So distance, how do we take distance, right? So is it S should be at distance 0 because it is 0 like neighbors or links away from itself. A, B, and D are like 1 link away from S. B, E is like 2 links away. F is like 3 links away. So I think that's how the links distance works.
The next group, at least the vertices that I did visit, C and E, they're all the vertices where I have to take 2 steps. They're all the vertices with distance 2. And then at the very end, vertex F, that is one of distance 3.
Okay.
So unlike DFS, which kind of tries to find very long paths at the start, I kind of slowly expanding my search space. First, looking at all the vertices that are first the start vertex is kind of closest thing I can have distance 0 from this thing. Then I look at the ones with distance 1. Then I look at the ones with distance 2. In the end, I have this closest vertex distance 3. And in particular, if I look at only the green edges, those are kind of the 3 edges, similar to DFS. So green edges from shortest path S to each other vertex.
Okay, so green edges form
And
the
it's kind of
shortest
relying on the fact
paths
that
from
when I construct
S to
the
every
edges,
other. Okay,
I
fine,
can
fine,
only
fine.
visit
Hold on.
in things in sequence of distance. So the one observation here is that observation for all E, another D and follow property, PFS visits all vertices of distance at most D for visiting vertex of distance D plus 1. You can actually prove that this is true. It's basically proof when that's over the digit.
So there's a very important observation.
Intuitively, the idea is that how could I get?
Hold on. Let me just put this down. Right. Cool. So observations that I'm noting down on a piece of paper are from S to every other vertex, I guess. And this is again a good observation for all D that belongs to my N. So distances, like distances D, PFS visits all vertices of distance less than or equal to D before visiting a vertex of distance D plus 1. Okay, hold on. Let's think very carefully. Okay, hold on. So $6:30. Oh shit, it's 6:30. I need a virtual joining link, I guess. Ah, come on, dude. This is so annoying. Annoying. Okay, I need to install multipass via Brew first of all. That's later on. So annoying, dude. So annoying. Go on. Cool. Let's see. For all distances that I can do, that makes sense because yeah, makes sense. If there is a cross edge though, can I say that D, like for example, if S had an edge from S directly to C, we know C is at distance 2, but we could perhaps say that because there's directly an edge and it's like the first node gets to pick its neighbors, it will say it's a distance 1. Okay, makes sense. I get it. It holds true.
The vertex that is part of the listening assistance to me, how can I add this to my queue? I can only add this if I first manage to visit the vertex that's closer. So distance 2. So that's kind of how you can formulate the inductive circuit if you want to prove this.
Alright,
basically, if you have a network with DNS, you can figure out inductive circuit if you want to prove this. Add this if I first manage to visit the vertex that's closer. So distance 2. So that's kind of how you can formulate the inductive circuit if you want to prove this. But basically, if you have a network with DNS, you can figure out the shortest path. If you have any shortest, like the fewest number of edges you have to take, the fewest number of steps you have to take, each path. So right now, this happens because, at least in my pseudocode description, I'm only checking the visitor thing that I call something from the queue. If I were to add a check here, then I would not add it again. The reason why I'm doing the check here is that there are some other algorithms where they, for example, use priority queues. It's kind of important that you can add something multiple times into the queue. Maybe later you add something again to lower priority. That's going to be important later. For BFS, it actually doesn't matter if you have this visitor path here or here. If you were to do it up here, you would not do the same thing over again. So let's say I add something with a high priority first. I don't, here I'm adding something with high priority, and somehow here I'm not marking it as visitor or anything. I'm not doing visitor check or anything. Later, maybe I'm adding it again with lower priority, and then it gets stuck. This I'm actually going to do that thing as an example right now in the next algorithm. Question was why do we keep adding the same vertex over and over again to the queue? It's because I don't have any check for being visited yet. And for the next algorithm, that's going to be important. So let's look at the next algorithm. So this here gives you the shortest path, where shortest means the smallest number of hops, the smallest number of steps you take. But maybe the edges don't have the same length. Think of something like a loop network. Let's look at a longer street than this one. So wouldn't that take more time to go up this edge? Wouldn't it create some distance value on every edge? So let's look at this example here. Say I have my start vertex S, next another vertex C, the vertex B, and these edges here, they have weights or costs or lengths assigned to them. So let's say this edge here, maybe going along this edge takes 10 minutes, going along the edge at the top takes 5 minutes, and going along the edge at the bottom takes 3 minutes. And now I will ask, okay, what's the fastest way to go from S to C? If you run BFS, and with an S, it adds both of these things to the queue. BFS will tell me the shortest way to go from S to C is to just take this thing because it's one step, but this takes 2 minutes. But yeah, BFS doesn't accommodate the fact that maybe edges take a different amount of time. So actually, the faster route would be to take this detour over B, because here I only need total 8 minutes, right? First 5 minutes here, then 3 minutes here. So what we care about is to find the shortest path now, where short is not defined as the smallest number of steps. Instead, we don't care about the sum of these weights.
What happens if you just move the edges into like 10 different vertices? You know what I'm saying?
Right. Right. We could do something like split this into lots of small vertices, and then BFS would solve it, correct? One problem is that, what if this cost here is a million? Now we have a million vertices here, and then that makes your algorithm quite a lot slower, because BFS is going to visit every one of these single small vertices. So we would like to have something where the complexity scales, and the small vertices that we have, it doesn't care about the fact that it has a target rate here. So, problem that we want to solve, find shortest path.
Hold on, I missed some of that.
Right. We could do something like split this into the shortest path, where shortest means maybe going along this edge takes 10 minutes, going along the edge at the top takes 5 minutes, and going along the edge at the bottom takes 3 minutes. And now I will ask, okay, what's the fastest way to go from S to C? If you run BFS, and with an S, it adds both of these things to the queue. BFS will tell me the shortest way to go from S to C is to just take this thing because it's one step, but this takes 2 minutes. But yeah, BFS doesn't accommodate the fact that maybe edges take a different amount of time. So actually, the faster route would be to take this detour over B, because here I only need total 8 minutes, right? First 5 minutes here, then 3 minutes here. So what we care about is to find the shortest path now, where short is not defined as the smallest number of steps. Instead, we don't care about the sum of these weights.
What happens if you just move the edges into like 10 different vertices? You know what I'm saying?
Right. Right. We could do something like split this into lots of small vertices, and then BFS would solve it, correct? One problem is that, what if this cost here is a million? Now we have a million vertices here, and then that makes your algorithm quite a lot slower, because BFS is going to visit every one of these single small vertices. So we would like to have something where the complexity scales, and the small vertices that we have, it doesn't care about the fact that it has a target rate here. So, problem that we want to solve, find shortest path. From, let's say, S to every other vertex. And the important thing here is that the length of the path is the sum of edge weights. Okay. And using this definition for the length of the shortest path, we can also define the distances between the vertices. We say that the distance from some vertex Q to some other vertex B, that's the length of the shortest path. From Q to B. Okay. So So we want to modify BFS so it can kind of make use of these edge weights. And one of the reasons why BFS worked was this observation that it first visits everything of a certain distance before going to everything of a higher distance. And now distance is not the number of steps, but the edge weight. So maybe it just makes sense to use distance as our priority. Because let's say I have a priority queue and I just say, always pick the vertex with the smallest distance from my queue, then automatically it kind of tries to first visit everything with the smallest distance. So idea, use same algorithm.
Oh, but when you're popping from the queue,
Just use the distance
okay,
as priority.
it's pretty good to be honest. It's pretty good to be honest.
So let me just copy paste the pseudocode.
Huh. Pretty good. Man, I'm sleep deprived. But we gotta push. We gotta keep pushing, baby girl.
So same algorithm as before, but we need to use a priority and we need to compute distances. So let's have the following lines. So I'm adding U to my queue. Let's also save V as like the parent where I'm coming from. Let's use the, let's add distance from U plus the cost to V as our priority. This is parent, this is priority. And also adding the following. When I pop something from my queue, I'm getting the vertex that I want to visit, and I'm getting this parent where I came from. I'm going to say, let's store the distance of my vertex V. What's the distance? If I'm coming from this parent, then the distance is first, I needed to reach my parent, and then I have to take one extra step, some edge from the parent to V. That's the extra cost I'm paying. Add the new lines. This is new, and all of the extra is not new. Sorry? This is different, and I'm adding the.
So the queue
Right. I do get the parents, so that also changed here, yes.
Hold on, I missed something. Hold on. What the fuck?
I'm going to say, let's store the distance of my vertex V. What's the distance? If I'm coming from this parent, then the distance is first.
He has something already. He's just copy pasting it below. And then he's gonna okay. Hold on. This while he explains, I'm gonna write this shit down, Oh my god, dude. Alright. Okay. Okay, so let this be on. I'm just gonna mute myself real quick while I attend a meeting. I'll be back. So
So same algorithm as before, but we need to use a priority and we need to compute distances. So let's add the following lines. So I'm adding U to my queue. Let's also save V as like the parent where I'm coming from. And let's use the, let's add distance from U plus the cost to V as our priority. This is parent. This is priority. And also adding the following. When I pop something from my queue, I'm getting the vertex that I want to visit, and I'm getting this parent where I came from.
God damn it, dude. That was such a long fucking meeting. I think it was like an hour or so, more than an hour, dude. Like it started at like 6:34. I hate useless meetings, but it has to be done, I guess. Cool. Continuing with the lecture. Continuing with the lecture, I'm just gonna use my thick Indian accent. Sorry, I should be more focused. Should be more. Uh, let's see. There's a fucking mosquito here, which is like annoying me, but whatever. We want to thank you for making this your home and so on. Okay. Whatever, bro. Mang, Fang, or whatever. Is 94 LPA too much in Bangalore? Or whatever, bro. Okay, anyways, cool. The 5 notifications is out. Hold on, just gotta quickly do one thing. Real quick, right? No. Yeah. Pretty good, bro. That's pretty good. 16, that's ages ago. 7 years at Meta is wild, bro. Mania, bro, that's fine. I have an elevator. I'm just reaching out to a recruiter. My bad. I gotta do this because. Hold on. Let's see. I need like an elevator pitch. Job prep reflections now. So it's an MSCS certainly. Okay, fine. That's fine, I guess. Man, I need to get better at like bit manipulation. That's just fucking. That makes sense. So. Okay. Okay. Systems that serve over 200 million users. Okay, so saw your push about meta hiring. Okay. The battery is low. I'll gotta charge it. Cool. Does this look good? I guess. Okay, fine. Let's do one thing. Let's shut up, dude. Shut up, dude. Okay, I need to charge this. I have like 2 more hours of somewhat productive work that I can maybe do if all goes well. If no one comes to distract me, that is cool. Let's continue with the lecture. Let's see how the stream strength is. It's excellent. It's excellent. It's good. It's good. Cool. So,
I'm going to say, let's solve this is this. Oh my God, V. Ability. V has like the parent where I'm coming from. Let's use the this text. This is U plus the cost. V has ability. This is parent. This is ability. And also having following. When I post something from a queue, and I take a look at the business and I take this parent where I came from. I'm going to say, let's solve this is this. Oh my God, V. What's the distance? If I'm coming from the parent,
it's gonna distance of the vertex v is gonna be distance of parent plus the cost of uv, essentially.
and the distance is first, I needed to reach.
It's the same thing as priority.
And then I would take one extra step, some edge from the parent to V.
Oh,
That's
yeah,
the extra
yeah.
cost I had.
That's perfect.
The new rice. This is new, and all the extra is new.
Okay, so you get parent and this cool.
So, this is different, and I think I do get the answer. That's change. This change, and this change. Okay, then I need to pick the lowest priority.
So if okay, this is probably a heap. It's just a mini heap.
Don't I already get this distance here from because that's the priority. Yes, so this is what you do. Well, not that later. You need to have you need to compute this. Okay, let's just run an example, see why this works. We're going to look at the same math before. This is my code. This is the graph. I have my ability to use, and I draw here down the Q.
I do need to pee, so I'm probably gonna like pause this for a second, quickly go and pee. And I hope no one tries to bother me or take my stuff from me when I'm peeing. Yo, beers. Okay, hold on. So okay, I'm back. Cool. So we have like some 40 minutes of dedicated study, I guess. Cool, I'll be back in a sec. Just gotta pee. Okay, I'm back. Disconnect. Why the fuck does this automatically try to like sneakily Yo, I'm back. I got like a fuck all mosquito bite. It's a fuck all asshole mosquito that tried to bite my ass. There's a bitch ass mosquito that tried to bite me, bro. Anyway, so let's go. Okay, I'm back. Cool. So, yeah, let's go through this again. Can I rewrite the algorithm on my own? Let's see. That would be a good test, right? Like, so the shortest path algorithm, I'm gonna try to write it myself, right? So, shortest P takes in some argument V, right? And now it starts a Q. I'll just call this Q, or I can just call this min heap. Cool. I'll just call it like a min heap. Oh, you know what? I just want to stick to something like normal. I know it's a priority queue. Priority queue or a heap. This is what it is. Now I will simply do q dot append v. Now while q v then parent, then cost edge equals q dot pop, get the lowest priority node, if visited of v is true, continue. Visited of v is true for neighbors u of v, q dot append. We will append a tuple now. We'll append. Did I just kill a mosquito? I hope I killed the mosquito, because that motherfucker was. So the thing is, it's easy to kill a mosquito, okay? I'll be very honest. But it's hard to kill a mosquito. Like, mosquitoes aren't like very good at their. Like, they're not as good as houseflies when it comes to avoiding getting swatted or swapped or something. They're shitty. The motor skills are pretty bad. But. Okay, so U goes in, then its parent, which is going to be V. Then it gets a distance of U, which is the current neighbor N, plus cost of the edge UV. This is what it gets. Now, we know that we need to again also add distance of V. We need to update this. This is just gonna be like distance from its parent. So whatever is the distance from its parent plus cost from parent to some V. This is what you gotta get here. I know I'm just using like, okay, you know what? I'll just be consistent and use small V's everywhere. Right, just for the sake of consistency. This is how I would say my shortest spot algorithm. Now I can do a hand run and see if something is wrong, but my point is okay, hold on. Hmm. अबे अबे यार my bad, my bad. Okay, this is what I think should be the algorithm. Just for the sake of consistency, I'll be like v comes first. Or actually, I could just do parent to child. So this is what I'll say my algorithm is. Let's see if this is right or if I'm missing anything here. Let's see. Hold on, is my audio good? I'm just gonna go here and quickly check if my audio is okay. अबे यार ठीक है, my audio is good, bro. Okay, cool. So I did q dot add, which is perfect, right? Then I did while q not empty, which is good. Okay, so one more mistake that I've done is this is very Python specific. TAs, graders may not be familiar with Python. So this is like, I would say, call it mistake 2, right? So I'm just gonna call it mistake 2. Mistake 2 is, in my pseudocode I wrote while q instead of while q not empty. I cannot assume that the graders know Python syntax. I have to explicitly state the syntax. I have to explicitly state the condition in natural or mathematical language. So mathematical language is like more rigorous, so it should be recognizable. Then I did v parent q dot pop while q not empty, v parent q dot pop, makes sense. Then I did if visited you do next, and next, otherwise you do this. You add distance equals distance parent plus cost parent v, which is correct. Then you did uv, then distance u plus cost uv. Perfecto. So cool. So just to add a few more, I guess. Yeah, just yeah. So v is parent and last value is cool.
And then I start and go to CD and then not have any So initially, my brother said this was just.
Oh, there's a mistake number 3 that I didn't check. Yeah, let's just call this mistake 3. This, okay, hold on. This should be q.append v null 0. So the start of the queue is okay. when pushing the very first node in the queue, I should have put instead of, okay, so I'll just do this, but I'll do a strike through. How do I do strike through, bro? Hey yo, shut the fuck up, bro. Format, how do I do strike through, bro? Yeah, perfect. Cool, so this is how I would call this. Next.
Yes, I don't have that element, so I will zero. That's my queue. I pop up my queue to see the element. So I am visiting S. And now I'm adding an element to my queue. What do I add? I don't have the vertex C, the element S, and my logic is going to be this million. And I'm also adding the vertex E to my queue. So the vertex with the lowest priority value to the vertex. So I'm adding the vertex C again. This element E, and here the distance is now going to be 5 plus 3, which is 8. With the lowest value and this time I do another iteration and I stop. The first time I added the C above the this the first time to choose vertex E from something like from up. We have also that's 96. Yes. Okay, so I'm going to put next twice the thing this is naming.
Oh, nice. I love it. Cool. So, revelation time. Is just Dijkstra's algo. Woohoo! So this is okay, cool.
From S everything else. I need to compute the correct value. So when I give this small, I can reach something like negative cost.
Negative number, Dijkstra's leading.
I can also when I give this small.
If it's a negative number, Dijkstra's leading is more efficient to continue cycling.
Okay, so that's almost like extra small. If I have a negative, that's something then so from S, I could reach something like negative cost. To measure that keeps my hand on the again. Yes. But it also be too small of a negative. It's almost that you probably is always actually like 8.5. Yes. So what I'm doing is always like 8.5. Not necessarily but 8.5 exists. Because it's basically improvement. This is if I have some analytics, what's the short from here to here? It's 0 because that doesn't move. Just the same there. Initially the distance is definitely correct. Yes. Yeah, I can do that. And the distance of the sign is always the distance of the
Okay, there's another thing. Okay, so this is like a note. Function takes in a single vertex S source, and we denote v only inside the while loop. That will be like cleaner, I guess. Yeah, this is better.
So I choose this already. This is the links of maybe I'm pushing that is your too big. That's what I want to do. So I'm going to prove that this is by action. And what does execution? So I assume the algorithm did not work. It's somehow like that algorithm makes a mistake. Assume the algorithm stores incorrect. This is the value. So there is some entry in my data that has one of it's not actually this, it's not actually like the process. So if that happens, let's just look at all the vertices that are graph. Let's say B1, B2, all the way to N. These are all the vertices that my algorithm visits, and this is all the vertices. Or which algorithm visits vertices. And let's say VI is the first one where I make a mistake. Okay. Because I make this assumption that the algorithm didn't work out. The algorithm made a mistake. If it didn't make a mistake, then there must be some first vertex that is the first and the last. So that means that this distance of, let's say, Vj is correct for j less than I. Because this is about the sequence of the vertices. The first few vertices is the correct distance value, but it's somehow I make a mistake. So the first vertex is correct, then I have something incorrect. And I want to bring that to completion. I need to have the data on that. That can change. And so this is my start to draw a picture. Which is idea of why this is not happening. Let's say I have my graph here. This is my graph here. Somewhere here, I have the vertex S. And there is this range of vertices that colors is green because it's everything that we're fine. So all of these is like vertices. Such as D1, D2, all the way to E I minus. These are all vertices that I actually plot and assign to correct value. And now, for some reason, there is one vertex. There is only I, but I now store incorrect value. Must be outside of this area because everything in this area was allowed by irregulars. This is the first one to the incorrect value. If the text represents that vertex, then there is some edge. There is running from inside this area to outside the area.
Hold on.
So I have to replace this for this guy, and somehow I must assign it to a value.
Let me paste a screenshot of this in the doc and see if I can perhaps complete the proof myself, right? Like, it'll give me a good test of my understanding of the subject. So assume that the algorithm stored an incorrect distance value from vertex 1 to n, and that is the order in which the algorithm visits these vertices. And we know that Dijkstra's algorithm, which is like the shortest path, is going to visit vertices which are closer to source, not closer, which are less costlier from source than any other vertex. And we are saying that let vi be the first vertex where distance of vi is wrong and vj is some vertex less than I. And we have created a boundary here which is vi. Okay, so we have assumed that there is a boundary vi plus 1 which is like all correctly ordered, what does it mean to say that Vi lies outside of this green region? It means that Vi is, uh, we did not visit Vi. We messed up the order of Vi. We decided to visit Vi on a later time, right? And we are assuming that the rules of the algorithm are the same, but the outcome is wrong, is what we are arguing here. So, a counter example of this would be to say that there is another path. Vi can be reached from S, and say Vi is somehow longer or like more time consuming than some other path that is also reachable via S. Can I perhaps argue that there is, okay, so in order to reach Vi minus 1, distance Vi minus 1 is wrong, but distance Vj is right. Or in fact, distance, okay, sorry, my bad. I was a little distracted. So, okay, so the argument here is that, यार क्या बकवास argument है भाई. Okay, sorry. We need to be more focused. Let's actually even forget the professor's diagram here. Let me just go to very first principles. Right, you are saying to me that you continuously the algorithm has produced the shortest distance till Vi minus 1. These are all short, but for Vi the distance is somehow larger. Now what does that mean? That means that there is more than one way to reach Vi, right? So okay, hold on. That could mean that essentially means that I have some V of I. Okay, so I have some V of I, and the distance of Vi that is stored, say, accounts for path. So we know this is essentially just distance of Vi minus 1 plus cost of some parent edge U, some parent to Vi, right? This is what it's gonna do, right? And we are assuming that the cost to this is somehow the parent that we are choosing to visit this with is somehow worse than some other points, right? Now the claim is everything before Vi minus 1 is correctly visited. Everything before Vi is correctly visited. So suppose there is an alternate path, right, that is essentially doing Vi. It is also doing some distance. Suppose it's like taking two routes, maybe like from here and here, like one arrow here and one arrow here. I don't know if it's gonna be inside of that green thing or outside, but maybe somewhere else, right? Some distance Vk or something, and then some parent k or something. So this is again one way, and we are saying that the distance, this distance, so we know it always go for the minimum one, right? The algorithm is gonna go for the minimum one. We're just saying that the output is gonna be wrong. So the algorithm is gonna, if I look at these two arms, the algorithm is gonna pick one which is shorter, right? Algorithm is gonna pick one which is shorter. Now, can I disprove that this, if I can somehow disprove that this path is shorter than this path, then I have disproved this assumption by saying that, hey, my argument is incorrect, right? So, okay, hold on. So let's see. How can I say that there are what other ways to reach to VI? Is it the case that I have to, like, I know VI minus 1 tak ka distance is perfect. Now, does it mean, uh, okay, and we know that V1 to Vn is the order in which the algorithm visits the vertices. So we know the order is fixed. We know the order is fixed. We just know that the order till Vi minus 1 is fixed. And we are essentially saying that there was another order, perhaps, which was, which could have taken us through some Vk node, like it would have. So we know distance till Vi is correct, right? This is correct for sure. We're assuming that the nodes are all positive. The edge weight is always positive. We know this is gonna be the constant term. The only thing is, like, when I take a path where I take a fork where I go from here to here, then like if I go to some VK, from VK I go from VI to VK. So this thing, right? Like first I will have to do okay, so this should have been like V of I minus 1, maybe. I don't know if this is going to be Vi minus 1. It's just going to be anything, right? It can be just anything. It can be just parent, right? Can it be? It's the order in which we visit the vertex. Yeah, it can be anything. We don't have to visit a vertex sequentially. We can just visit the vertices like randomly, depending on whatever has the lowest cost. We are essentially saying that whatever parent, okay, let's just call it parent X because it's like showing some X here. And I'm saying that there is some distance Vi. Oh, I don't think I should be saying distance this, but I should essentially be saying distance Vx, because since X is the one that is taking me to the next cost, this is what I'm doing. Vi minus 1 does not matter to me. It's just that I just know that Vx is less than Vi. Like X is less than I. That's all I know. Right? Now I'm saying that there is another path where I do like some distance Y plus a, so distance till Vy, like shortest distance till Vy, then some, and it goes through, like, suppose the path is S something something X and then Vi, and suppose the path here is S some Y, then some Z, and then this, right? So I'm saying there's this Vy will come with its own distance. Vy will come with its own distance, which is which it will come with its own cost, right? It will come with its own cost, which is whatever is yeah, I think it's just gonna call it, so Vy, right? So Vy, so from Vy to like whatever is Vz, this is the cost that gets incurred. Then plus we know this, so we assume that Y can either be inside or outside. What happens if Y is inside? Let's just say Y is inside and Z is outside, and we can just take all cases, right? So say Y is also less than I, Now, what about z? If I say z is also less than I, then it gets reduced to this case, which is not what I think is right. Now, there's a presidential debate watch party where they're giving free pizzas. Come on, dude, why am I missing out on this? But I've already eaten one meal for the day, so I'm just eating like a single meal a day, so that should be honestly sufficient for me. I do need to have my protein shake before I sleep, because we gotta stay hydrated. Shiz, I need to refill water. Okay, anyways, let's get back to our argument. So I know that there is vi, which is like bad. Now let's say there is some vy and vz that are also inside, which are also less than I. Then I'm saying that there is a cost. There's this distance vy, which I know is better, which is like smaller, and then there is another edge that is vy vz, which is like another cost. And now if I claim that vz lies inside this green boundary, then it means that I am okay. So if z also lies inside this green boundary, then I'm essentially saying that this is just distance. This is just adding on the cost of and if I'm assuming that z is smaller, like I'm assuming that y to z is like an optimal thing, then I'm essentially saying that if I'm just saying z to v I, then you can say that this entire thing is equivalent to the above case if both y and z are inside, right? So this makes no sense. This is the same as the above one, because we're saying that everything before this was perfect. Now what if z was outside of this boundary? If z was outside of this boundary, then I know that this distance is perfect, right? This distance is perfect. But I am saying that my algorithm should have picked something wrong, should have picked a higher cost. Like I'm saying everything after I is just wrongly visited or like is an incorrect order, then I'm claiming that vy should be visiting a wrong or a costlier node first so that it reaches vz. But this, I don't know, I'm kind of, it's kind of still inchoate in my head. I'm not very concretely able to form an argument, but I think it has to do something with one of the vertex. It has to do with like an alternate path that goes to vi, and that alternate path, one of the vertex of the alternate path lying outside of the green boundary. But let's see.
So let's say this thing here, this edge. This is the edge used by the extra.
Yeah, sure, excuse with extra. Fair.
Meaning this is the edge that's optimized by the Q. And claiming, but I also find this is very nice. So the method of x is here, let's say, from s to x. Then I take this extra step from x to the somehow that's not the process now. This is also the process of x. But taking this last step is incorrect. If it's also the process, then there is another thing that is the relation now. This is another object, something that somehow was from s in some object to I, which is correct process. And this is again outside the green cycle. This is how it's sometimes must cross inside the green area of the green area. Then I see some vertex, so there's a vertex A, this is a vertex E, then I'm crossing the common edge inside the common spectrum.
Okay, this is so far good. I'm crossing it. Okay, I get it. So if the vertex was inside of my boundary, then I'm claiming that. What am I claiming? Yeah, I'm claiming something. Cool.
Correct was the path somehow my algorithm discover this correct was the path. There must be some edge that doesn't really interfaces linear area and everything is direct to some subjects. That's the area. And this is the true of the path. So the distance that I stored. So this is the distance that I stored for the vertex. I stored the distance to this vertex plus the cross of x di. I just store this is the length of this path here, some part of x and x plus that. And somehow when I assign this here, it's a bad choice. So somehow this thing must be bigger than the direct distance from S to I. That's one thing. What do I know about I? Bigger than the direct distance. So the distance that I stored.
Hold on, we gotta recap.
This direct of the path. There must be some edge that doesn't really interfaces linear area and everything is direct to some subjects. That's the area. And this is basically true of the path.
Fair.
So the distance that I stored. So this is the distance that I stored for the vertex. I stored the distance to this vertex plus the cross of x di. I just store this is the length of this path here, some part of x and x plus that. And somehow when I assign this here, it's a bad choice. So somehow this thing must be bigger than the direct distance from S to I.
Fair.
That's the one thing. What do I know about the actual resistance? What is the actual resistance? It may not be resistance to this. Using the property of the resistance to this. So the correct resistance should be the resistance from S to vertex A plus the cost and going A to B plus the distance from B to I.
Fair. This is what I got too.
The first half of SA, this is what is step and one of those remaining classes. What can we say about the the distance from B to I? What do you know of us? Do you know anything of us?
Okay, so what do we know about distance from B to VI in the context of this thing? So we know that distance from B to VI is okay, the true shortest distance from B to VI should be that B is shorter. Sorry, the distance from B to V is shorter than distance from X to V. Is that what we are saying? Is it shorter than distance from X to VI? Oh, okay. So like we know distance cost A, that's like fixed, and distance cost A plus cost AB should be like greater than, I don't know.
Just this is some of the remaining things
Some applications here. And which is control of quantity. So if now the description is to give me anything else. the distance from B to GI. What do we know about this? Do we know anything about this?
Just this is some of the main things in that, right?
Some. Some of the yeah.
That is true. We do know that is some of the. Oh, so that's okay. So I did not consider that observation. Although it's so trivial that I did not consider it. Like it's the sum of all edge weights. I did not consider it because I thought that is not the way to go, and I think that's like a flaw that I cannot ignore the most trivial observations. It's sum of all the edge weights. It's like a very important observation, but I weighed it very low for some reason.
And so if now the restriction is say all x is positive, then that means this thing is a sum of all positives. So I know that this should be zero. But it needs to be defined that I have positive edges. If the graph
Fair.
I need to basically enter the graph as maybe it's a measure of negative cost. Then I can actually find something here that is that means I have this as a technical. That's something that's positive. What do I know about this value here and this value here?
They're the most optimal and shortest path from source.
Notice that if I find values these values, that means I have this as a technical. That's why I have this these things already. Because I'm going to this that's my values. And I can answer this. Anyway, this is a good text. All the names that I do to you. So A was positive. Then B is that to you. X was positive. B I was to you. What do we know about the which vertex is going to be removed from Q? Smallest one. So somehow our hierarchy decided to remove this here from the Q before we make this part. That will tell us that one is smaller than the other. And that the distance of x plus the cost from x to I, that is less than the distance to A plus the cost of A to B.
Come on, dude, that's a very stupid proof. Like, I thought that it would be more rigorous than this, but it's literally this. Then I get it.
You see the relations. So here, I think I want to tell you that tells me this is here, this is has some things to us.
Hold on, so XVI, so I'm just really quickly gonna rewind back a few seconds. So just to like add like the more updated thing here. So distance VI should be less. It shows. Okay, so maybe I'll just write it down here. So the fact that, okay. Z is outside the green circle. If, okay, one subtle mistake that I did was I was focused on right order of visitation, and that's not the case. It's all about the true path rather than the right order. It's such a subtle like reorganization in my knowledge. Very subtle, but I caught it. If priority queue algo works right, then Z should have been popped before X which is not the case here. So disprove. Is that all the proof is? Killed a mosquito. I'm so happy. So okay, so we essentially said that okay, because
Here, anything of what you that's the this is here, this has something to discuss. This is thing is bigger than this is the same plus the cost into do. So what I'm saying, this is x plus this cost. This is bigger than this, which is equal to this, bigger than this. And this is saying this is bigger than this. But here I have exactly the opposite. I say, oh, actually it's bigger, it's smaller.
oh, okay, hold on. It does get more rigorous.
So what I'm saying, this is x plus this cost. This is bigger than this, which is equal to this, bigger than this. And this is saying this is bigger than this. But here I have exactly the opposite. I say, oh, actually it's bigger, it's smaller. But it can't be bigger and smaller at the same time. So they make my relation.
Ah, okay, hold on. Got it. Deduction 1. If correct path is S, Y, Z, D, but algo gave S, X, D, then we are saying distance till y plus cost of y z plus cost whatever is z d is less than distance of x plus cost of x d, but we know from priority queue that smallest value is popped first, so priority queue asserts the exact opposite, that this other distance, or rather I could just say that this and these are fundamentally like opposite claims, right? On one hand you are saying, yeah, makes sense. I got it now.
Let's use this opportunity for argument. So bottleneck path here we also have hashtags.
Okay, bottleneck path is the next one. So I got that extra thing. Hold on. Just writing down the proof. Need to work on my handwriting for sure. Let's see. I just want to quickly check if what all subjects are gonna be there on the exam. Are there gonna be okay? Proving correctness is fine. F50 should be fine. Okay. Okay, the other algorithms from the class will not be a focus. So bottleneck prims A are okay. So bottleneck prims and A's and spanning tree are not part of the exam. So okay, so everything after this is just not part of the exam. But I'm just gonna quickly go through this. Sure, makes sense. Man, I need to also get printouts for my posters, but I'll do this in the morning, I guess.
This. And let's say my hashtags are 12, 11, 10. I don't care about the shortest path. I want to make sure that the smallest extract is as large as possible. For example, if you think of this, let's say I am some post office, maybe some post center. This is my headquarters, and I want to send stuff to other people. And I don't want to send too many trucks. And these edges are bridges that I have weight. And this bridge can carry almost 10 tons, and this bridge can carry almost 12 tons. So if I have to send a truck that is weighing 12 tons, and send them along the bridge terminal. So I want to find a path where I can send as much weight as possible. So here, taking this route, here I can send at most 10 tons. But here, if I take this graph, I could send 11 shots.
Got it. That's just the lowest edge is.
So I can't send 12 because if I send 12 once, then there's a break and a send length of the path to this. And what should we change here?
So I know Dijkstra's wants the shortest path. What if I look for the largest neighbor? Like I know it's 10, but if instead of like min, I just pick the largest value.
Suggestions. So instead of the lowest priority value, we want to have the highest priority value. So not a very short path, something that's more long. So highest priority value. Also looking at the algorithm. And for us, currently the distance is the sum of the edge max. Just looking at the distance of the path.
Mm-hmm. Oh, instead of that's actually a good point because I'll keep using the largest thing. Hold on.
And for us, currently the distance is the sum of the edge max. Just looking at the distance of the path. So the distance here, the minimum of the minimum, exactly. So there's a sum subtracting here the minimum.
Min of, okay, so distance is going to be the minimum of the parent.
That's it. So I think you can see now how a lot of these path problems, they want to have properties. It's all more or less the same algorithm. You just need to play around with what is the distance and do you want to what's going to be there.
Okay, so the distance part does not, okay. Right, so let's see.
Just looking at this is the path. So we just
So we're not adding, it's just like minimal.
And that's it. The same algorithm. Application. Entry. And one way to compute this is to observe that our algorithms that we computed here, they all construct trees. If I go, say, to the first example, I have this big graph, then what I'm constructing is just an tree. All they do is connect it, and they don't have any cycles down the line, because that's the big part. But in the DFS case, usually we love this tree and because I'm not constructing a tree. So for minimum span tree, we want to construct a tree based on our algorithm, but we want to have edge weights as small as possible. So just going to take the next algorithm. We do it have distance in it. And once you these edges as small as possible, right? Done. This is what trees are.
Okay.
So all these algorithms is basically the same thing, just change your hierarchy. Okay, then let's go to something that's a bit more exciting. We talked about finding close paths to the next algorithm. Question started to can I join and make this again? I TLS, this is my thing. So that's the next. Then I have some optional thing based on this. It's an algorithm that is used a lot for all the different decisions to perform in the state. You pick them. HU is something they call it.
Okay.
Okay, inside this distance, compute the distance was. You check the one downside is basically proof of from text algorithm doesn't work anymore. The heading of the change the distance was. The heuristic you could use, for example, is in the expect distance, like you to really reach the correct key. Very high idea of X.
Cool. So the deal is we have completely watched all the lecture material related to graphs and traversals. So what we're gonna do now is we will go through Piazza and open sample test on graphs over here, and we'll try to solve it real quick. Do we see this? Cool, we see this. Let's see. So MCQ. So we have this graph. Would the adjacency matrix representation of this graph be symmetric? A matrix is symmetric for all indices ij, where value at I j equals value at a ji. So I know that if I were to quickly calculate, will it be symmetric, as in if I switch the diagonal, will it be the same? So I know that there is I just wanna like have a piece of paper to solve the exam. So I'll just do S B E C F D H T. I don't know if why they have such a big question here. S P E C F D H T. I'm wondering if I even have to go through these things, but so if I go to SB, like edge of SB is 1. So edge of SB is gonna have like some point, some value, but will edge BS have any value? No. So it's like immediately I can say the answer for 1 is no, right? So so let's just do something like we'll just do paste this here. Okay, let's just do this. Mock test on graphs and traversals. So this is 1A is no, is what I'm saying. 1A is no, is what I'm saying. 1B, 1C, 1D, whatever, however many there are. Consider the topological sorting G. A topological order is just the post order. How many nodes could be the first node in the topological sorting if for some graph ABCD is the topological sorting, A would be the first. Okay, so how many nodes will be the topological start? So I know for a graph to have like a topological order, there needs to be a way to reach all other nodes. Like, so I know that S is one way to use to reach all other nodes. So I'm leaning towards 1 because I can immediately see if there is another source node. So I know other ways to reach T, yes. Are there ways to reach H? Yes. Are there ways to reach F? Yes. Are there ways to reach E? Yes. B, C. The only node that does not have an incoming edge is S, and we know for a fact that the topological sort, topological order orders everything from like left to right. If there is nothing that is coming in, then this has to be the leftmost edge. So it has to be 1. So I'm going to go with B is 1. Now let's go to C. Dijkstra's algorithm started on vertex S, so X is first. Each vertex visited only once. The node H is visited when. So Dijkstra would, of all of these, it's gonna visit all of these, right? These are all added to the priority queue. Then I know for a fact that of these 4, B's neighbors are added first. So visitation, right? So S is visited first, but these are all n queued. So then B was visited second. Then B's neighbors were also added, which were like E and F. So between E, F, C, D, and H, E and H are what we need to like figure out, right? Uh, so I know the way Dijkstra's algorithm is gonna work is it's gonna do. Okay, hold on. I'm just gonna write this down real quick. So S was first in the queue. Next in the queue were B, C, and D. What was popped out of the queue? B had the shortest length so far, so B was popped out because it had a length of just 1. So B got popped out. And what were the neighbors of B? They were E, which is like distance 2, F, which is at distance 5. My C was at distance 4. My B was visited. D is at distance 9. So 0, 1. So B was visited. Now of 4, 9, 2, and 5, I think I'm going to visit E now because E is shorter. So E is second. What are E's neighbors? E's neighbors are T, which has a distance of 11. There's nothing else for T. Then there is C that I am visiting, right? So I visited C, and C's neighbors were F, which is 5, right? C's neighbors were F, which is 5, and H, which is 8, right? So C was visited third. Then the fourth thing that was visited was F, right? F was visited the next because F had 5. So F was visited fourth, and F had edge T, which was 5 plus 4, which is 9. So T got updated to 9. Now between D, H, D, F, and H, so H was visited 5th. So I will say 6th is 5th. I'm just gonna do this real quick again. So S is the first. S is 0 distance and visited first. S added B, C, D, which had the distance 1, 4, and 9 respectively. Then I second visited B, which is 2, and then B added E and F. So E had 2 and F had 5 because 1 plus 4 is 5. And then I decided to visit E the third. So E added T, which is 2 plus 9 is 11. So E got visited. Then the next thing to get visited was C, which is visited fourth. C added F, which is 5. So that's the same thing, right? She added f, which was visited fifth, and the cost was the same. So 4 plus 1, 1 plus 4, the same thing, right? So 5, and then what did we have next? C had another edge called h, which was added eighth. And what is it that, okay, we want to find the h node, right? So h was added, right? Then the smallest thing was f. So f was added. Okay, so f is traversed fifth. This just updates my t and says that t can be reached in like 9. So this is good. Now the smallest that I can visit is h. So h is actually sixth. Sorry, my bad. So I'm gonna call sixth, right? Took a long time, should not. If the graph were undirected and minimum spanning tree could be formed, if this graph were undirected, a minimum spanning tree could be formed of how much weight? Undirected. Okay, cool. If this was undirected, then I know you know what, I'm just gonna like take this, copy this, like copy this. Alright, so paint online, right? Yes, cool. So I added this. Now I'll just use a brush, the largest size. I'll use like white ink. Perfect, this works, right? So uh, I know B, the shortest path to B is just this. So these three paths are always going to remain the same, right? So 4 plus 4 plus 4. So these are not like directed edges anymore. So I can just assume that there's no arrow here, but I can freely remove arrows that are useless, right? So for B, um, I do have till h everything, and h was whatever 8. 8 plus 1 was 9. So one way to do a spanning tree was like, is this the fastest, the shortest path to reach h is actually 4 plus 4, 8. So I can get rid of this shit. So yeah, I can get rid of this shit. I can get rid of this shit. Right? I don't need to use this path. And the fastest way to reach f is via this or this, which is the same thing. So I'm just gonna be like 1 plus 4 plus 4 is 9, but this plus this plus this is this. This is fine, I guess. This is just 9, so I get rid of this. This is fine. I don't need this shit. Right? I don't need this shit. I know minimum spanning tree is not a topic for exam, but whatever. Right? So I'm just gonna like make this a little pretty. Cool. So h is this. Now the fastest way to reach t. So I know that this is not the fastest because this is 11. Just gonna get rid of this shit. Right? We don't need this shit at all. Yeah, getting rid of this should be good. Yeah, so now for these two, I can get rid of any edge because it's just going to be the same thing, right? And now if I do a plus, it's going to be max sum, right? So it's going to be like 14 plus 4 plus 9. So 13. So 7. Okay. This graph was undirected MST. So my answer is nowhere in here, right? Which is kind of funny. So I know that the shortest path to E. Why do they say that a minimum spanning tree, right? So maybe I should have studied minimum spanning tree. Isn't minimum spanning tree just like weight of? Is minimum spanning tree the path from the longest to the shortest? No, right? So I know that the shortest path to D is anyways going through. Oh, are they claiming that there is a path out there that is shorter than 9? Like, for example, 1, 4, or 1, 4, 1, 4, 1, something. Or this has to be the smallest, right? And the minimum spanning tree is just the same as Dijkstra's, but you just pick the shortest edge first. Shortest edge first. Okay, I know the minimum spanning tree is like you pick the shortest edge. You queue all the shortest edges first. Hold on, I'm just gonna create a minimum spanning tree real quick. I know it should have been faster than this. So I added SB, which is 1. I added SC, SD, 4 and 9. Then I added whatever is the smallest for after B. So these were like uh, BE, I guess. So BE is 1. This is like 1 plus 1. And then 1 plus 4 is what? 5? Okay, I think I'm trying to figure this out though. So I know it's like 1, 2. So I did this 1. I said, okay, the smallest in this is still these. So I add the edges for this. It is still 1. So 1, 1. So it's just 2. Now I have 4, so I just add one of the 4s. And then I have another 4s. So I just add 1 here. So 1, I guess 1 plus 1 plus 4. So 1 added, whatever was 1 added again. Then I checked what was smallest. So there's some 4, so I just picked 1 4. I picked 1 4. There's another 4, 1 that I could do. I did 1. And then out of 4, 1. So I did plus 4. Oh, I get it now. So if I were to like, my bad, bro. Yeah, this is what I'll do. I'll go to paint. I'll use the white color. Yeah, now I'll just say that. Okay, hold on. Yeah, cool. So I go to 1. I go to 1. So it's like 1 plus 1. This is the 1. Now I check what is the next smallest edge. Say this is the 1. Right? I add this. It goes to this. It says this is already visited, so it just ignores this. It ignores this. Now this is just 1. But this only wants to go to the visited one, so this has this. It's just 4s everywhere, so it just can go to anyone. It goes to this one. It goes to this one. Now it says this one is like kind of counted for, so it just gets rid of this one. It gets rid of this one too, actually. And instead I have reached this one, so I'm gonna get rid of this one too. And then it gets 4 plus 4 is 8. 9, 10, 11, 12, 13. So I would think my answer is 13. So it's just gonna be D13. It took me a long time because I had to like reconstruct or rethink, or from first principles I had to like do minimum spanning tree, but this is what I think my answer would look like, I guess. Let's just do this. I guess this is what I would say my minimum spanning tree would look like. I'm just gonna say min span tree would probably look something like this. Cool, cool. Guessing. Okay, is there another one? No, guys, it's just MCQ. For each of the question below, check the box that and explain your answer for. So there's just 3, right? 4 of them, right? D. Cool. Now do point A, do point B, do point C, whatever, however there are. Give a counter example or a short 1-2 sentence explanation. For every valid topological order, there is some way to break ties, such as depth first search will produce, such that depth first search will produce the topological order. Okay. For every valid topological order, there is some way to break ties such that depth first search will produce a topological order. Okay, so they are saying that if there are 2 topological orders, there exist some ties in which this would hold. Now, if I just pick a simple graph, which is just A going to B, going to C, going to D, and then there's like a cross edge where A decides to go to D first, and none of them are like, say, okay, all of them are directed graphs, okay? And topological order is like the exit order, right? Like the exit order, like the way to go from left to right, right? Just orders everything from left to right. And I know there are multiple valid topological orders. This is actually a really good question. This is actually a really good question. I'm gonna mark this for review. I'm gonna solve the easier ones in true or false first. 3 is another one. Bipartite graphs are. We'll come to this. We'll come to this first. There's only one negative weighted edge E in graph G. We can find the shortest path through G by adding WE to all edge weights and returning the Dijkstra's and running the Dijkstra's algorithm. So only there's one negative weight, and we say that there is essentially one edge that has become positive, right? Now it has become 0. And what are the implications of negative? First of all, why is it that negative values can be scary for Dijkstra's algorithm? Because you could run into a path where you could. Okay, so the reason why negatives are bad is because we expect the distance that is updated to be a sum of some values, right? Now, if there is a negative value that we have been given, we know that it's a non-increasing value. So it could essentially say that, hey, it could get stuck in a loop. That's one, right? It never gets to my solution because it just keeps repeating. But it wants to do visited things, right? It does not say that, hey, I can't. If it's visited something, it'll say fuck you, and it should work. But why is there a focus on having positive edges, right? So I have Dijkstra's. So I have some source, right? And there is some X. There's some VI that I'm visiting. So S, X, and say VI. That's how I'm visiting it. Say this was negative, right? And there was a Y plus VE, then X would essentially obviously give this one out first because it's like a negative edge. And then because this is a negative edge. It has reduced the distance positive. It has to be positive, right? There is one negative weighted edge E in the graph. You can find the shortest path through G by adding weight of E to all edge weights and then running Dijkstra's. You know what? I should not be like randomly skimming through these questions. For each of the question below, check the box and explain the answer. For every valid topological order, there is some way to break ties such that depth first search will produce a topological order. So I'm just gonna create a topological order. So if A goes to B, then goes to C, and there's one way to do this, right? So I know if I do my depth first search such that A first visits B, then visits C. There is also a depth first where it chooses the other path first. And say there's a back edge to B, right? And A chooses C, which in turn chooses B. So C exited first, but then B exited, so if a value is essentially, if I know that in a if I know that, I'm just thinking in DFS, right, we will always update our post order. Right, so if I review my DFS notes, if something is visited, doesn't matter what happens, we always, while exiting the function, we update it. So in the first one, we're doing A, which goes to B, which goes to C. So C exits last. And if C, okay, so sure. So this is topological order 1, topological order 2. For every valid topological order, there is some way to break ties such that so the break ties is essentially happening between these two. Like I could have taken the path from B, A to B, or A to C. Okay, so I know that the way to break ties is essentially Okay, so is there a topological order that depth first search cannot produce? The goal is to order all edges from left to right, correct? Now, is there a topological order that DFS cannot produce? So, I know in these two orders, DFS is able to just pick one of the two paths, and then it means that, hey, I've been able to reach that particular node. And if I can say that it's a valid topological order, it's a valid topological order, and if I say that uh, okay, so I've been able to reorganize this question in my mind a little better now. So I know for a fact that a topological order is the is essentially arranging all your vertices such that they go from left to right. Now the question is, uh, sure. So if you give me a set of topological orders that can be produced by DFS, it's just like picking different children to move. There's some way to break ties. I can do that. Now the question is, are there topological orders outside of this set? If there is something that cannot be is a topological order but cannot be produced by DFS, then that's going to be a very interesting question. So let's see. A topological order orders everything from left to right, which implies that there is going to be some node that gets visited the very last. Now I'm saying that what is the property of DFS? It's going to, can there ever be a DFS? Is BFS in general considered a topological sort? Let's Google this. So this is new knowledge. Can BFS generate topological order? So we can use either DFS or BFS. And I do know that there is some BFS algorithm. For example, okay, let's see. If there is some, if it's a topological order, right? So if it's like, it's a directed graph. A goes to B and then goes to C. And that is a topological order, right? So there is one order where A went to B, which went to C, and then there was one order where A went to both B and C separately without linking them first. So there is an evidence, there does lie a possibility that in BFS, if there was a traversal in BFS, we probably would not be able to reach it via DFS. Let's construct an example for this, right? DFS will always do connected nodes. It will not do adjacent level nodes, right? So suppose I had A. Okay, I'm just gonna draw this in MS Paint, I guess. File. Yes. Can I save? Why did I save this? I don't want to save this. Sorry. Okay, so suppose I have this node A, and I have B. I have C. I have D. I know the value for the thing that BFS is good at is essentially uh, like I know that there's a topological order from BFS that can be like uh, so let's see. So DFS is gonna go through this edge first, then recurse and go to this edge, and then go to recurse and go to this edge. If I construct an example where it is forced to sure, this could work, right? Like okay, undo, right? I sub Suppose I had some edge E here, right? And then I had this, right? This is like my undirected graph. Now DFS would go to A, B, E, then C and D. So A, B, E, C, and D. And my BFS would essentially do A, B, C, D, and E. Can DFS ever produce this order? Can DFS ever produce this topological sort? I go to D, I go to E, I go to C, I go to B. I go to D, suppose I started with this. Okay, I have to start with A. In DFS, I wanna do this, so I wanna go with B, but I am forced to recurse here, right? I cannot say that I will refuse. So okay, so I have constructed a counter example, so I will now say no because I have a counter example. Hold on, I'll just say B. Okay, B F S and then D F S. So I know for a fact that this counter example shows, this example in general shows that the path below cannot be generated by DFS, right? So I'm just gonna be like, gonna say false. The following BFS. Yeah, this is also left to right. Order cannot be generated by DFS. So that's why it's false. Next. There is one negative weighted edge E on graph G. We can find the shortest path through G by adding weight I to all weight W. Okay, so वो weight add करके D की तरफ चला रहे हैं. So okay, let's go back to the drawing board. No. So the reason why Dijkstra works is I have some point X which is taking me to like say VI, and there is another point A that takes me to B, that takes me to VI. We are saying that the distance, this distance, so we are saying that distance to this plus this edge is smaller than this. That's why it's Dijkstra picked this one up. If this edge is negative, we are saying that Dijkstra could get stuck in some sort of loop. Okay, if there is just one negative edge, right? Like what happens if we have a single negative edge, right? So if you have a single negative edge between these two, suppose you just have, and you know you're not supposed to visit, go back to like a visited algo, right? Like if I go back to my notes here, if I go back to my notes here, I know this is Dijkstra. I know if it is visited, I don't visit it again. So even if it was like negative and visited, I would not visit it again. But there is some assumption that we do on addition. We say that it's all strictly positive, right? What is happening on adding a single negative edge? Like, can't a number system be so simple that negative edge itself was my starting point and everything else was just increasing, right? So we are essentially saying that there is going to be some path which if has a negative edge, which if it has a negative edge, it's gonna give a shorter path, it's gonna give a shorter distance to x than a and b. So I have vi over here like this. Let's see, I have vi over here, something like this. Why am I crying for this? Like, why is this such a complicated thing for me? A negative edge in Dijkstra's, right? Can we find the shortest path through G by adding weight to all edge weights and then returning Dijkstra's algorithm? You're just making it positive. But if we go back to the definition of Dijkstra, which is here, you are not doing min max anything, you just take distance plus cost of that parent, right? Here also you're doing distance plus cost of that parent, and you're gonna possibly get an edge after something that reduces the cost further. Hold on, so I'm saying that if this is, say, 1 minus 100, and I say this is 1, so I pick both of these. This is, say, 9, I don't know, random numbers, and I say that, hey, you know what, this edge is very small. The distance till this is like minus 100, and then because it's like minus 100, it's gonna keep adding. So suppose because this was minus 100, it prioritized something like this, said it's 100. I don't know, for this question I've somehow hit a cognitive wall. This has to be simpler than this, right? Maybe I can just do a simple example. So no, right? So say I do a simple question where S, B, and C, and this takes me 5, this takes me 3 initially, this takes me 10, for example. I know I prefer this path. If I make this minus 10, and if suppose there was a back edge here, right? Then ideally Dijkstra would be like, hey, I see this has like a negative 10 thing. So 5 plus negative 10 is still negative 5. So this is still faster than, I know it's visited, but let's for the sake of argument, say this is just 0 or 1 maybe. So I did 5, 1, so it's like negative 4, it's 5, 1, 10. Negative 4 is still faster than this. And this is fastest till C. But then it could perhaps like try to keep, it can't keep looping because there is a exit statement. It's like, hey, but let's formally see why can't handle negative 8s. Let's see. Okay, so weight is found as negative. Dijkstra from A will first develop C and will later find A, B, C. Oh, I see. I see. So negative weights are not bad. It's just that Dijkstra will not find the optimal path. Oh. Oh. Oh, this is such a clever. Oh, so there was one mistake in my thinking. Hold on. Mistakes that I made. On negative weights or graph weights in general, I tried to reason very hard against the very presence of weights in my algo. Okay, weights in my graph. I spent a good chunk of time trying to rationalize why negative weights in any graph would not give me the best answer. In reality, it's gonna be a shortcoming of the algo and not an inherent flaw in the graph. Negative edges are really desirable in the graph. Shit, I was just looking from a very fixed lens. So what is this hidden biases, prejudice, assumptions about the nature of the problem? Right, so I know for a fact that so Dijkstra is essentially just not able to find the most optimal solution, right? And it says if I add W amount, so if I had a graph A, two, 5, again, something like this. Yeah, B, C is minus of 10, I guess. Then I say that this is shortest, but this is closed. I can't do B and C, but B and C is faster because this is like minus 5. What happens if I make this 0? Right, make this 0. Can I construct any example wherein I say I know negative essentially means that I am making it shorter, but if I add explicitly 0, then I'm essentially saying that even if I go with greedy paths, I can assume that the distance is either going to increase, even if it doesn't increase. For example, if these two were the same, suppose these two were the same, I know the path, either of the paths would still be correct, right? Doesn't matter if one is optimal or the other. So even if Dijkstra chooses something else, it's still going to be optimal. The only point is that Dijkstra is greedily going to pick the smaller edge first. And we were saying that the moment I remove the negative weights, you're first picking a weight. you did not have the ability to see in the future that weights suddenly decrease. So you were happily, greedily picking weights, whichever was the minimal one. And as soon as you found a weight that is zero, what happens? You are not, can I say, the paths before them are picked greedily. So if there was a path, there is just not going to be a cost added to this, but so there's just not going to be any cost added to this extra node. If I added a node from A to C, which is like some length x, and I say that in order to reach C, the jump from x to C is smaller than jump from x to C is currently smaller. If there was a suddenly insanely large negative weight here, I would have marked C as C and then not come here. But if I say that there is a weight here that is going to be, there is a chance that this becomes smaller than the other one, this argument holds. This means that I can't do this. In fact, any negative value is not the point. It's just that if it had a negative value, we could have constructed an argument where it reduces. It essentially means that after oh, holy fuck, I get it now. Dude, I get it now. We can essentially construct this and say that I picked A and I picked two routes to C. This is route 1. This is route 2. This is 2. This is 5. In case of negative edges, we are saying that after I picked this, I had the ability to make this lesser, potentially negative or potentially smaller than 2, right? So I had the ability to make this. So it's like after I traverse, I say I want to update this. But when I set this value to 0, it means that, hey, you have traversed here, but you can no longer update this. So I'm just going to say B is true. B is true. This is true. I know we're running late. I know like we gotta sleep now. But let's just solve the last one real fast. And we'll check the answers. And then 3 and 4 we'll do in the morning, I guess. Consider the graph GVE where E belongs to edge that is used by minimum spanning tree of G. There's another edge E belonging to E by T of the same weight as T. We can always differentiate minimum spanning tree T dash by replacing the edge E with E dash belonging to, okay. Consider a graph is used by minimum spanning tree T. There is another edge E dash belonging to E of the same weight as E. I didn't get this question honestly, so I'm going to skip this. You're given, we claim that the following will prove that if there is some path from source to T is like target, I guess. The distance UV in G is a path with distance UV between S and T in H. Okay, I have to like go through this proof Excel algorithm and actually correctly find distance S T in G. Fine, this can just be the same. But let's open the solutions. I just want to at least confirm my first few things. Cool. So I'll just quickly go here. So let's quickly see what our answers were. Did we have a C? I didn't get C. Like no 1, 6th, 13th. So no 1, 6th, 13th. So the first are right. And then we had Then we had false and true, and then the last one we didn't know. So false and then false. This one I got wrong, which is sad. Interesting, I've kind of fucked this up. And I didn't get the last question at all, so to figure this out with this, why did I get this wrong? With edge A to B, B to C, or the weights can be sure. So A to B has 1, B to C has -1, A to C has 0.5. Oh, you're updating the weights essentially. Oh, I get it. It's a good argument. Like 0.5, 1.5, say A to B is 1, B to C is -1. So 1 minus 1 is 0. Weight is 0.5, 1.5, and then 2. So it just goes to